Okay, so now I want to show that every finite extension is a composition of simple extensions, and I kind of want to do with tower properties, right? Um, so finite extensions are simple, right? So and actually the big theorem, I guess, the biggest theorem that we can do is the following, right? So this is like what's called the primitive element theorem, and what we're going. So the spoiler is the following, right? Is that the spoiler is that if so let F be a field, and let's say K containing F a finite field extension. Okay, so the theorem is that there exists some alpha in K such that K is equal to F adjoin alpha. Okay, so this thing here is called the primitive element theorem. So this is the primitive element theorem. Okay, and so this is the primitive element, and so like in practice, right? We'll have things like, you'll have things like, I don't know, Q adjoin, I don't know, some crazy roots alpha 2, right? And then it turns out that like 90% of the time, and then there's some special conditions you have to check, that this works, alpha 1 plus alpha 2. Okay, I mean it's really 99% of the time. Okay, or maybe I should say 100% of the time. Okay, but this is how this is going to go, and we're going towards this. Right. So the first thing to do is to show that we can reduce finite extensions to a bunch of adjoining a bunch of things. Right. So let's do that first. Okay. So so first let's fix some notation. So let K over F be a finite extension. Or I mean, it doesn't need to be a finite. It just needs to be an extension. Be an extension. Okay, then let alpha 1. Okay, so then what do we mean by this? So the field. Okay, so if alpha 1 through alpha r are elements of K, then we have the following. So then F of alpha 1, alpha 2, alpha r. So what do we mean by this? We mean that this is like F of alpha 1, then we join alpha 2, and then we kind of keep going, and then we join alpha r elements. So we just kind of like successively adjoin more elements. So this is, we kind of just keep adjoining elements. And let me just kind of make a little remark here. Remark. So the order doesn't matter. Okay, so you could, yeah, F adjoining alpha 1, then adjoining alpha 2 is the same thing as F adjoining alpha 2, then adjoining alpha 1. All right, so this is something that we could do. Okay, so what I want to say now is, so this, it's really like a composition. So this thing here is really a composition of simple extensions. Okay, so or basic, maybe we should call them basic extensions. Oh, I kind of regret the word simple extension because it might mean something else. Okay, so let's not, yeah. Okay, so it's a composition of okay, I'm now going to call these basic extensions. So basic. Okay, because simple might correspond to something called simple groups later, and now I'm like regretting this. Okay, but let's just call them basic extensions, or like primitive extensions. All right. Okay, so let me state the theorem. Okay, so the theorem is the following. So the theorem is that if k over k containing f is finite, then there exists some alpha 1 through alpha r such that k is equal to f of alpha 1 alpha r. So every finite extension is really made up of a bunch of basic extensions. Okay, so the point of this is that the point here, the point finite extensions are made of basic ones. All right, so let's do that. All right, so let's do the proof. Okay, so here's the proof. So what we'll do is we just kind of like, okay, so since, all right, so let's do this. It's really easy. So since k is finite over f, is d, this is less than infinity, we have some v1, so vd in k, linearly independent over f, such that k is the sum of these things. Okay, so every element can be written as an f linear combination of these dudes. All right. So then, so what do we have? So now let's consider. All right. So we consider. Let's call this k naught, which is f, and now we allow ourselves multiplications between all these things. Okay, so not just sums. So this thing here is a field, and this is contained in k. So we just kind of like take all the rational linear combinations of this. So we have some intermediate field, and it's clearly contained in k. Okay. So conversely, right? So this is the so we have one direction here, and then I'm going to just show the other. The other direction is easy, right? So conversely, conversely, since k is since let's call this star. Well, k is clearly contained in this big thing, right? And so we have that k0, or so this is at k0. So we have k0 is contained in k, and k is contained in k0. So this implies that k is equal to k0. Right? That's all there is to it. All right. Okay. So now what do I want to say? So I just want to say one more thing about the behavior in towers. Okay, so this is behavior of degrees in towers. So suppose that we have a sequence of finite extensions. So we have L, it's contained in K, it's contained in F. Okay, so suppose they're not equal. I mean, they don't, actually, this doesn't even need to be true. They could be equal. Okay, then we have this formula that's super useful. It's that L over F is L over K, K over F. Okay, so this is the proof. All right, so sorry. So this is saying that the dimensions behave in this kind of nice formula here. Okay, so we have finite field extensions, then we have this formula. Okay, so proof. All right, so what we'll do, the proof idea is essentially that so let's write L. So L is equal to, okay, there's one way to do it. So L is equal to K1, or sorry, KW1 plus KW, let's say N. Okay, so we're here. Let's give some notation here. So this thing here is equal to N, and this thing here will be equal to M. So this thing will be N times M. All right, and what we do is we just kind of write out bases. So L is this thing. So this is a basis, right? And then K looks like FV1 FVM. Okay, and then this is a K basis, this is an F basis. So in particular, so F linearly independent elements K linearly independent elements are F linearly independent. Okay, so the basis is the following. So the basis, so L here, L is now equal to FV1 plus FVM W1 plus FV1 FVM Wn. Okay, and so this tells us, this formula here, okay, so this gives us, so the candidate basis, F basis for L is that is this VI WJ, where I, so I is between 1 and M, and J is between 1 and N. Okay, so all right, so that's what we have here. All right. All right. And so I guess I need to show that they're linear. So we need to show that they're linearly independent. Okay. So we need to show. Oh. So we need to show independent. Okay. So if not, so if there exists some Cij, if there exists some Cij's in let's say F, such that the sum of Cij Vi Wj, this is 0, so that we have to sum over i's and j's, and i's or j's are in this range up here. Okay, so if this is 0, so then this implies that, well, what we can do is we can just sum over the, so this will be the sum over, okay, so we'll sum over j's, and then we sum over i's, Cij Vi Wj. Okay, so ij, so this is 0. Okay, so now these guys are elements of K. Okay, and so since since these, so since the Wj's are K linearly independent, right? So that implies, so this is a K linear combination, right? So this gives us that each of those things here. This implies that for each j, sum of Cij over I of Vi, right? So this thing needs to be equal to 0. Okay, now we just disentangle this again. So by linear independence, by F linear independence, the sum of so this tells us that that these CI's need to be equal to 0. So C 1j is equal to C2j is equal to, and this needs to be equal to C, and then how many of them do we have? Mj's. So this needs to be equal to 0 for each j. Each j. And so so hence therefore all theCij's are 0 for all the i's and j's in the appropriate ranges. So this is 1. Okay, and hence this proves that this VIWJ is a basis. As we vary over the j's, this is a basis, is an F basis for L, and it has the right cardinality. So we're done, right? And has cardinality, or has cardinality n times m. All right, so that's the proof of that. Okay, so it remains to prove the primitive element theorem, and I'm not going to do that right now.